So we will be discussing August 2025 algorithms quiz paper solutions. Now let us consider the first question. So you are given an unordered list of n distinct integers. What's the minimum number of element comparisons required to find an integer that is not the second largest? And similarly, what's the minimum number of element comparisons to find an element that is not the third smallest in the list? To solve this problem, let us take three elements from the list. If and find the smallest of those three elements. Now the claim is smallest of those elements cannot be the second largest, because at least there are two elements which are greater than that. So that cannot be the second largest. So the number of comparisons required to find that is 2. Similarly, to find an integer that is not the third smallest, take 4 elements and find the largest. Now that largest cannot be third smallest, because at least 3 elements which are smaller than that. So the answer for this is 3. So the final answer is 2, 3. Second question is, solve the recurrence relation T of n is T of square root of n plus log n. Now this is not in the general form. To solve this kind of recurrence relation, we have to use a trick called variable substitution. Substitute n by e power x. Then we'll get T of e power x as T of e power x by 2 plus, if you substitute log n e power x, then we'll get x. And consider T of e power x as s of x, then we'll get s of x equal to s of x by 2 plus x. So now this is in the general form of the divide and conquer, like T of n is equal to a into T of n by b plus n power k, and this is where a is equal to 1 and b is equal to 2 and k is equal to 1, and a is less than b power k. When a is less than b power k, it is order of n power k, that is order of x here. Now if we take s of log n, then we'll get T of e power log n, and e will cancel out, then we'll get T of n. T of n is, as we know that s of x is order of log x, s of log n is order of log n. The answer is order of log n. Now the third question is scheduling. You are given 5 jobs with the starting and ending time are given, and we have to schedule such that the maximum number of overlapping jobs should be completed. So the greedy strategy here is select the jobs as per the finishing time such that it should not overlap with already selected jobs. That means we have to select a job with a minimum finishing time first. So here we will be selecting A, which finishes first, and then next turn we will be selecting B, but B overlaps with A, so we will ignore B. Next we will select C, and next we will be selecting D. So the answer is A, C, D. Now the fourth question. So we are given x as sum of squares of n natural numbers by ignoring 0. Now how can it be asymptotically represented? With the asymptotic notations theta, omega and big O. That's the question. Here we are given theta of n power 4, theta of n cube, big O of n power 5 and omega of n square. Which one of those can be represented with a x? Now as we know that the sum of squares of n natural numbers is n into n plus 1 into 2n plus 1 by 6, that is some constant into n cube, and we can ignore the lower order terms. Now this n cube is less than or equal to some c into n square. We can c into some c into n cube, some c into n power 4, some c into n power 5. So the upper bound can be written as order of n cube, order of n power 4, order of n power 5. With a big O notation, we can write it as this, and with a omega notation, we can say that this n cube is greater than or equal to some c into n cube, or c into n square, or c into n, or c into log n. So we can say the lower bound is omega of n cube, omega of n square, omega of n, so on. Now the tighter bound, that means when both big O and omega are used, then it is theta of n cube, because in this case n cube and n cube are there. So the tighter bound is theta of n cube. Now the answer is except the first option, remaining all holds, because theta of n cube holds, big O of n power 5 holds, omega of n square is holds, because n square is less than or equal to n square is less than n cube, n power 5 is greater than n cube, and n cube is equal to n cube. That's so we can easily see. So the answer is D. Now the fifth question. Fifth question is, you are given an array of n integers and a function which takes array of n integers, and in every pass it compares two adjacent elements, and if the first element is greater than second element, it swaps. That means if it is not in ascending order, it swaps. So now you are given 16 elements, and which are distinct, and the first 8 elements are negative numbers which are in ascending order, next 8 integers are in positive in descending order, and they are asking you to find out the number of swaps required. Now to solve this problem, what we do is, we will consider a smaller input. We will consider for 6 integers. So in 6 integers, 3 must be negative numbers which are in ascending order, which are already in ascending order, -3, -2, -1, and the remaining 3 elements are in descending order. We will consider 40, 30, 20. Okay, and so for n is equal to 6, so there will be 5 passes, and then j is 0 to 4 minus 5. Now as you can see that as the first 3 elements are already in ascending order, there won't be any swaps, and from 40 and 30 will be compared, and there is a swap as they are not in ascending order. Similarly 40, 20 will be swapped, and there is a swap. Now after the first pass, you get this 30, 20 and 40 will be in placed in the correct position. There will be 2 swaps. In the next pass, similarly 30 will be swapped with 20, and 30 will be correctly placed. Then the number of swaps required here is 2 plus 1. So in general, for 16 elements, what happens is, you are going to do the actual operations on the 8 elements only. So for the 8 elements, there will be number of swaps is 7 plus 6 plus so on up to 1. So this is sum of first 7 natural numbers. So 7 into 8 by 2. So the answer is 28. Thank you.